That's exciting. I've been lecturing in a mask. Okay, great. Well, thanks to the organizers for having this workshop, your persistence in having this workshop. I'm really happy to be here. This is the first in-person talk that I've given in a long time. So the topic of my talk is, when do Dirac materials exhibit higher order Fermi arcs? So I will try to answer this question and also explain what the question means. So I'm going to be talking about Dirac materials. Clicker will work. Okay, great. So I'm going to be talking primarily about Dirac materials, but I wanted to show one slide on biofermions for contrast and also to get everyone on the same page. So what is a biofermion? A biofermion is a two-band crossing, which is a source sink of Berry curvature. And it's that last property which is extremely important because that's what gives it all of its topological properties. And so I list some of these interesting properties here. We get Fermi arcs, chiral anomaly, quantum oscillations that we wouldn't see in other materials. And I think the field of biofermions has really taken off because these phenomena are both interesting and unusual experimentally, but also kind of deep and fundamental theoretical interest. And so because these concepts are interesting both theoretically and experimentally, as well as this kind of unprecedented interplay in predicting topological biomaterials, this field has really exploded. Now, when we have crystal symmetry, we can get a wide variety of other types of excitations. So I've listed some of them here. Dirac fermions, which is what I'm really going to talk about, multifold fermions, generalizations of biofermions, and example line nodes. It seems like there's an ever-expanding space of these things. But I think one of the interesting questions is, are all of these symmetry-protected band crossings topological? I think that lately people have been conflating these two terms, and it's not clear that all of these crossings should be called topological. And so for certain types of band crossings, what I've shown on the left here, there's generalizations of biofermions, which are also sources of Berry curvature. So we can distinguish these types of band crossings into two types: those that are sources of Berry curvature and those that aren't. Those that are sources of Berry curvature will have Fermi arcs, and they have some clear topological attributes. So those we can all say are topological semimetals. But there's some class, such as Dirac fermions, which are not sources of Berry curvature. We can think of Dirac fermion as two biofermions of opposite chirality at the same place in momentum space. And for these, it's not clear what will make them, whether they are topological. So that's kind of the question that I want to address. So are Dirac fermions topological? At first, we thought that Dirac fermions had Fermi arcs. Like I said, we can think of this as two biofermions of opposite chirality on top of each other and protected by crystal symmetry. And since each biofermion has a Fermi arc, you might think that a Dirac fermion would have two Fermi arcs, which is what's shown in this upper middle picture. But in this nice series of works by Kargarian and company, they showed that actually this doesn't have to be the case. The Dirac fermion can have two Fermi arcs, but also these Fermi arcs can kind of split off and annihilate. So Dirac materials don't have to have Fermi arcs. So then you might say, well, there's no bulk edge correspondence. We shouldn't think of these as topological semimetals. On the flip side, as I've been saying, Dirac fermions kind of inherently know that they're made of two biofermions. And what I mean by that is, when you apply a magnetic field, they split into two biofermions. And so because they have that information inside of them, maybe we should still call them topological. Somehow they kind of know that they have these two different symmetry protected spaces, which are hosting biofermions. And so I can see arguments for and against calling Dirac fermions topological fermions. So last year, I think we shed some new insight into the topology of Dirac fermions, and by introducing this concept, which you call higher order Fermi arcs. And this gives rise to a bulk edge correspondence. So I'll explain what this means. On the left-hand side here, it's kind of hard to see my pointer. On the left-hand side, what I'm thinking of is a geometry which is finite in two dimensions, so it makes a square cross-section, and infinite in the third direction. Okay, and so the Dirac fermion, the Dirac points in the bulk will be 2 points in that, they have a well-defined KZ coordinate. If they were vial fermions on any one of these surfaces, we would see a Fermi arc connecting the projection of the 2 Dirac points. But we don't have Fermi arcs because they're Dirac fermions. But instead, what we can show, which I'll discuss, is that on the corners where 2 surfaces meet, if you take the projection of the Dirac points, there'll be a set of corner localized states that connect the projection of the 2 Dirac points. And so we call these higher order Fermi arcs as a generalization of higher order topological insulators. They have gapless features on corners where 2 surfaces meet. So the left-hand picture is trying to depict that. Those red lines are the corner projections of the Dirac fermions, and there'll be corner localized mid-gap modes there. The right-hand picture is showing a band structure for this. And so what I mean by that is my system is infinite in the Z direction, but finite in X and Y. So I have KZ as a good quantum number. So I can plot a band structure as a function of KZ. And I see these 2 crossings, those points where the conduction valence bands touch, that's the bulk Dirac points. And then I see this little extra line coming out. Those are the corner localized states. And that's what I'm calling these higher order Fermi arcs. And so I'm proposing that the topological nature of Dirac fermions is given by this bulk hinge correspondence. There's gapless modes, which are located on the hinges of this system. So now let me give a little bit of background as to how we can understand how this works. Like I said, this is motivated by a higher order topological insulator in 2D. And so the higher order topological insulator, or the quadrupole insulator, was proposed in this nice work by Benalcazar, Bernavig, and Hughes. And what they showed was that if you have the right collection of symmetries, you can have a quantized dipole moment. And if you choose that dipole moment to be vanishing, you're in some phase where it vanishes, you can also have a quantized quadrupole moment. And that quadrupole moment gives rise to gapless corner states. And so the way that I like to think about this, so as I've drawn on this left-hand picture, which is partially blocked here, but maybe you can see, if I have an insulator, I can assign a Wannier center to my valence bands. And in a trivial phase, so the Wannier center tells me where the electrons are localized. In a trivial phase, the Wannier center is localized on top of the atoms. So that's what this little Gaussian is meant to show. It's electrons sitting on top of atoms. But I can also drive a phase transition where the Wannier centers are instead localized in the center of these plaquettes, not on the atoms. And if I do that phase transition, what happens is that the bulk gap needs to close. And now the electron weight is not sitting on the atoms, but it's sitting on the spaces where atoms are not. So if I cut this system into a finite size square, then the electron weight is going to be localized on the corners of this square. And that's how I get these mid-gap corner modes. So this middle picture from their paper is showing that in one phase, this is a plot of the entire energy spectrum. In this kind of trivial region, you have a gapped insulator, and then the bulk gap closes. And then as you move into this higher order TI region, you see this extra band of red states. And if you look at how those states are localized in real space, they're localized at the corners of the square. So these are the corner states that I'm talking about. So our idea is that these symmetries, which can protect this quadrupole moment in 2D, are exactly the same symmetries that protect Dirac points. And so in some 3D Dirac material, we can look at 2D slices, and we can classify these 2D slices as being quadrupole trivial or quadrupole insulator. And if they have this non-trivial quadrupole index, then they're going to have corner states. And those corner states are going to exactly these higher order Fermi arcs. So in this left-hand picture, what I'm kind of trying to show is I have these 2 Dirac points. And at the Dirac points, the spectrum is gapless. But on either side, either above in energy, above in KZ or below in KZ, I have some 2D gapped plane. That gapped plane is 2D. It has all of the symmetry of these higher order TI in 2D. And so I can ask, does it have corner states or does it not have corner states? And the answer to that question cannot change as I consider adjacent planes. It can't change until the gap closes. So on one side of the Dirac point, I could have some index. On the other side, I could have the other index. But in between, it can't change. And so these So in the planes in between these two Dirac points, I have corner states and I have them for all those KZ planes. And so that's what's forming these higher order Fermi arcs, which are mid-gap modes localized on the corners, connecting the projections of the bulk Diracs. Okay, and then we have a couple of different examples of this, depending on the different symmetries that we have. So we can actually generalize the symmetry group. And so the nicest look, so on the top, I'm showing these bulk band structures. So for example, on the top left, I can see that there's a Dirac point in the bulk band structure. And if I plot this finite size rod band structure, I see the projection of the bulk Dirac points. That's where these, that's where the bands touch in that projection. And I see this kind of skinny line coming out. Those are the Fermi arcs. And if I looked at where those are localized, they'd be localized on the corners of my crystal. If I have time reversal symmetry, it's a little bit, you have the same effect, but what happens is that you also have surface states. And so that's at the corners of this plot, you see that the bands also close. That's actually a surface band closing, but you still see these Fermi arcs coming out of the projection of the Dirac points. And finally, on the right-hand picture, we consider the case without inversion symmetry, and that allows these corner states to split in energy, but we still see them. Okay, so these are some models that we made which exhibit these higher order Fermi arcs. Natural question is, can we see them in materials? And so then we tried to do these ab initio calculations. So the left is cadmium arsenide. Cadmium arsenide is one of the prototypical Dirac materials. So the upper left-hand picture is showing the band structure, and right where that zero Fermi line is crossing, you can see that these two bands cross, that makes up the Dirac point. And then in the lower picture is showing basically on these corners, those are the projections of the Dirac point. In the center, the surface bands crossing. But this kind of bright yellow line, the color is showing me localization on the corners. And so this bright yellow line is a little segment of states which are localized on the corners of this crystal, in which connect the section of the bulk Dirac points. The bulk Dirac points are where these white crossings are shown. And we see some similar feature in potassium manganese bismuth. So, okay, so we've established that we can see these higher order Fermi arcs, at least in theory, in simulations of materials. But the question that remains in our previous work, we only looked at Dirac points that were protected by fourfold rotation symmetries, like cadmium arsenide. But the remaining question that we want to answer is, how does this work for other Dirac materials, which are protected by 3 or 6-fold rotation symmetries? And this is a particularly relevant question because, for example, sodium bismuth, which is one of the other prototypical or first predicted Dirac materials, has a 6-fold screw symmetry. And it wasn't obvious, at least at the time, that if you had 3 or 6-fold rotation symmetries, how this higher order TI would work. It's a completely different symmetry group, and it wasn't studied in the work by Benalcazar and company. So the question then that we set out to answer was, do all Dirac points exhibit these higher order Fermi arcs, or is it specific to the 2D higher order TI with the 4-fold rotation axis? And so the answer to this, which is the result of work with my student Yuan Fang, is what we found is that all of the linear Dirac fermions exhibit higher order Fermi arcs. So this is a definite, this bulk hinge correspondence is a feature of all Dirac fermions. And I think that gives it a topological nature that we didn't know previously. But in addition, there can be quadratic Dirac points, which are linear in one direction and quadratic in the others. This can be protected by symmetry. And these ones don't have the higher order Fermi arcs, basically because they can kind of be split into two linears. So there's 2 steps to proving this, and I'll just kind of try to sketch how this works in the next 5 minutes. So the first thing that we need to know is that corner charge, if you have a 2D system, whether or not it has corner charge is determined by the positions of the Wannier centers. So I tried to justify this before. If we have a trivial insulator, Wannier centers will be sitting on top of the ions, and then we don't get any edge states. But if we have one of these higher order topological insulators, I've drawn 2 different pictures. In this middle picture, So the Wannier centers are the black dots, the ions or the atoms or the blue circles. The middle picture is symmetric. It obeys the rotation symmetry, but it's not neutral because I have more ions than I have electrons. So that's probably a problem. Usually most crystals we consider are neutral. On the other hand, on the far right, what I've drawn is it's a neutral system. It has the same number of ions as it does electrons, but it's not symmetric. And so in this paper by Benalcazar and Hughes, they call this the filling anomaly, which is you have this mismatch when your Wannier centers are not sitting on your on your ion centers. You have this mismatch where your crystal can either be a neutral insulator or a symmetric insulator, but not both. And the way that this is resolved is by having corner states. When you have the corner states, you can partially fill them, and so you're no longer an insulator. So you can resolve this conflict by having these mid-gap corner states. And of course, these are the corner states that kind of define the higher order TI. Okay, so we can figure out corner charge from where the Wannier centers are, but we don't actually want to compute Wannier centers because we want to classify Dirac points, and we don't want to look at the full Hamiltonian. We just want to ask when two bands cross, how does this corner charge change? We don't necessarily even have a full Hamiltonian. So the next step that we need is that in order to determine Wannier centers, we can actually take a shortcut, which is we can just look at the symmetry of the valence bands. And the symmetry eigenvalues of the valence band can actually tell us something about the Wannier centers. And so I've drawn one example of how this works in case of fourfold rotation symmetry. On the left-hand side, for the trivial insulator, if your electron Wannier centers are sitting on top of your atoms, you'll have certain representations that appear at 0, 0 and pi, pi points, which I've written down here. But if your Wannier centers are not sitting on the ions, like on the right-hand picture, then these symmetry representations change. And the reason that they change is because if you do a rotation about one of these blue ion centers, you'll move one Wannier center into another. And that's related by translation. So you pick up a phase, and that phase directly impacts the symmetry eigenvalues. And so you can see from this little table that on the left-hand picture, the right-hand picture, I can distinguish these two different cases by the eigenvalues of the C4 rotation symmetry. So we don't actually need to compute Wannier centers. We just need to look at symmetry eigenvalues. Then we can get the Wannier center, and then we can figure out whether we have corner charge or not. And so putting these pieces together is exactly what my student UN did. So he derived this algorithm to compute the symmetry indicators for any type of symmetry. From the symmetry indicators, we get the Wannier center. From the Wannier center, we get the corner charge. And this is a non-trivial generalization of previous work. In previous work, they found the corner charge in an ad hoc way. We now have this very straightforward code where if you had any symmetry group, you could input the symmetries and input the different Wannier centers, and you could output then your corner charge for any group of bands. So that works immediately. And the other non-trivial generalization is that we considered having any number of atoms in the unit cell. In previous work, they only considered one atom in the unit cell. But it's really important to know where your atoms are. And the previous formulas will break down if you have multiple atoms in the unit cell. And the reason is because there's two reasons. One is wherever your atoms are tells you how you can truncate your crystal, because you can't chop through an atom. So it's very important to know where your atoms are. And the other is because where your atoms are is your definition of trivial, because trivial is when Wannier centers are sitting on top of atoms. So you need to know where the atoms are, and you need to be able to have more than one in the unit cell to accommodate all types of crystals. And so that's the thing that we've done here. And so using this result, this allows us then to classify the different types of Dirac points. So we have this little table that I've shown at the bottom, which is under work by UN. And let me just tell you what this table says. The first line or the first row is saying, if I have fourfold rotation symmetry, then I have a Z2 classification. That means if I cross a Dirac point, I go from having no Fermi arcs, these higher order Fermi arcs, to having them. If I cross another one, they go away. So that's how the Z2 classification works. But we found that there's something different for the 3 and the 6-fold symmetries, which is you have a Z3 classification. That just means that there's different types of Dirac points. And the reason is because there's 3 possible ERECs now instead of 2. you can call them A, B, and C. So you can have different Dirac points where A crosses B, B crosses C, or C crosses A. And each one of those will give you a different type of, they'll change the corner charge by 2. So you can go from 0 higher order Fermi arc to 1 higher order Fermi arc, and then you can get another higher order Fermi arc, and then go back to 0. And so we found that with 3 and 6-fold rotation symmetry, there's multiple types of Dirac points, and we know how to enumerate them. And so the consequences of this are, one, the question we set out to answer. We've now shown that all of the linear Dirac fermions have higher order Fermi arcs. That's a fact. But we've also shown that there's these quadratic ones that don't. And then finally, we can apply this to sodium-3 bismuth and show that since sodium-3 bismuth has a 6-fold rotation symmetry, it is amongst the linear Dirac fermions that do have higher order Fermi arcs. And so that's a testable prediction of our theory. Modulo, it's not entirely clear how to measure these. Okay, and so then I just wanted to say we made this tight binding simulation of sodium-3 bismuth to verify the existence of these Fermi arcs. So the top picture is showing the bulk, this rod band structure where the bands close is the Dirac point, and you see this line of states coming out. That's our higher order Fermi arc. And the other thing that I wanted to say is that classifying Dirac fermions is not new, actually. There's a few classifications over the past several years, and we've looked at these previous works, especially the first 2, which are older, and we found that our classification is not bigger or smaller than theirs. They're just different. Neither one is contained in the other because we're looking for different physical signatures. So I can say more about that to anyone who's interested. And this last one, I think, is actually really recent work, I think is on par, may actually be the same classification as ours. And then finally, there's another open question, which is beyond Dirac fermions, we have now these other non-chiral symmetry protected semimetals. Are they topological or not? And I can say a little bit more, but not that much more about it. I think there's still an open question. So in summary, I think we have some kind of new idea that these higher order Fermi arcs give us a bulk hinge correspondence for Dirac fermions that kind of confirms their topological nature. And we have to apply this to other types of semimetals, thinking about other types of bulk edge or bulk defect, bulk hinge correspondences that will help us answer this question of what types of semimetals are topological. So I'll end there. Yeah, thanks for your attention.
Robert, I'm wondering how you define a one-year center when you have multiple atoms in the unit cell.
Yeah, you have multiple Wannier centers. Oh, yes, sorry. So the question is, how can you define Wannier center if you have multiple atoms in the unit cell? And if you have an insulator, for however many bands you have, each one of those bands gives you one Wannier center. So you'll have multiple Wannier centers.
Right, but for example, let's say you have a multi-atom unit cell and you have electron probabilities on each atom, but the center of the Wannier function may be different, even though the probabilities of electron is on each atom, right? So the center of the Wannier function could still be different from the atom, right?
Yeah, okay, good. So I didn't actually write down, okay, so the question is, if you have multiple atoms in the unit cell, how can you define whether the Wannier centers are different from the atom centers because you have multiple atoms and multiple Wannier centers? I think, yeah, okay, great. So actually, I didn't actually write down this formula, but this filling anomaly can be cast in the following way. You can write it as a difference between number of Wannier centers at a particular Wyckoff position minus number of atom centers. So we don't have to, for each Wannier center, we don't have to associate with a particular atom. We can just take this set of differences. And so if there's any mismatch between, if there's say, 4 Wannier centers at one position and then 3 atom centers at that position, we just take the collection of these differences. And this is all defined modulo something. There's no, you don't need to associate each Wannier center to an atom. You have a collection of Wannier centers, a collection of atom centers, and you take these differences. And if there's any mismatch, then that mismatch will give you a filling anomaly. But the more atoms that you have, I guess probably the less likely you are to have a mismatch because if you had two mismatches, that would be the same thing as trivial. Yeah, does that answer your question?
We can talk later.
Yeah.
We can.
Yeah, so then I'm a bit confused about something very basic. Do you need fourfold or highest rotational symmetry to protect Dirac?
Oh, right. No. So what you need is a rotation symmetry. I'm sorry. The question is, what do you need fourfold rotation symmetry to predict a Dirac point? No, you need time reversal, inversion, and either 3, 4, or 6. You need a rotation symmetry. And the reason is because time reversal and inversion forces bands to be doubly degenerate. Okay, but for them to cross, you need to have a symmetry that allows them to cross. So twofold is not enough because there's the two degenerate bands, there's only one representation, so they will have avoided crossings. But a threefold symmetry or a 4 or a 6 allows you to have different irreps for these two degenerate bands, and then they cross, and that's how they form Dirac points.
You can't do it without at least.
Yes, so you cannot have Dirac points with a twofold rotation symmetry. It has to be 3, 4, or 6.
Ken, you give it a kind of a definition for topological materials as ones with both boundary.
Yes.
Corresponding.
Yeah.
Another possible definition is one that you know very well about adiabatic continuity of the atomic limit.
Yes.
And so,
Yeah.
is it, if we know that, for instance, these Dirac semimetals are not adiabatically continuous
Yeah.
with the atomic limit, couldn't we have said from that there has to be boundary states that are protected?
Yeah.
So we don't know what they are, but they have to be there somewhere.
Yeah. So this, okay. So to repeat the question is basically, what if we define topology as a as having an atomic limit which is not deformable? I'll say it this way: the Wannier center, your valence band are not deformable to an atomic limit. Okay. So the situation with the higher order topology is that you're deformable to an atomic limit, but it's not the atomic limit where your atoms are. Okay. Right. And so it's called, so it would be true. So then we ask about we need to refine our definition. Should we call that thing topological or not?
Yeah, I would say not topological.
Yeah. Okay. Maybe you would say not. And actually the reason why this is why the corner states do not connect the valence and conduction bands. They are sitting at, they're zero dimensional because they actually have a localization. So yeah, I mean.
If we consider that the definition is atomic, deformable to the atomic where the atoms are.
Yes.
Then do we consider that there are systems which are not deformable in that sense have to have boundary modes?
I think, yes.
We don't know where they are.
Yeah, I think that's basically the conclusion that we're reaching. So there's two, the cases are your Wannier centers are deformable to the atomic limit, and the atomic limit is where your atoms are. That's the most trivial case. Then we have a slightly less trivial case, which I'm calling topological, but I'm not tied to the word, which is that your Wannier centers have an atomic limit, but it's not where your atoms are. And that's the case where you'll have this corner charge. And there's some subtlety in modulo what, but it's all rigorously definable. Yeah, that's the corner charge that we're talking about. Since you're talking about now, but since you're still localized, it's corner charge, which is 0D, and it doesn't have this spectral flow that connects the conduction and valence bands. And then finally, we have the most strong form of topological, which is that you cannot make localized Wannier centers. You're not deformable to any atomic limit. And that's where you actually get kind of proper spectral flow of edge or surface, higher order TI then still has corner modes, but they actually flow and connect the conduction and valence bands. I think that's the hierarchy. Yes, and I think that's established now. Yeah.
So what you do is tilted. That two Dirac that show one possible position.
Yeah, okay, interesting question. So if it's tilted a little bit, then it doesn't matter. It won't affect this. If it's tilted all the way to type 2, yeah, I guess, yeah, I mean, I guess what I'm worried about is we need to have these 2D planes which are gapped. And if you're tilted over so much that you're type 2, I'm not sure. Yeah, it's always kind of hard for me to visualize that. I'm not sure if we can have 2D gapped planes. Maybe we need to define them a little more readily. If we can define a 2D gapped plane, then we can always ask what's the invariant of that 2D insulating plane. But I'm not sure if that thing is going to exist for type 2. Yes, that's an interesting point.
Okay. Yeah, maybe. And
Andrew.
So coming back to the model semimetals, let's for example with Dirac, so that one of the
Sure.
So following your
Yeah. Oh, yeah. So
and then
yes, great. So the question is basically, how can I, how should I think about the topological classification of Weyl fermions? Obviously, there's no gap, so we can't talk about deformable Wannier centers. And I guess the thing that we're saying here, it was already known for Weyl fermions. So in Weyl fermions, it goes as follows. Weyl fermions are gapless, 2D planes are in between different Weyl points are gapped, and those 2D planes can be classified as having a Chern number or not. And, you know, and since no symmetry is required, we need to talk about Chern number. And the Chern number, the edge states of each 2D Chern plane is exactly what gives me the Fermi arc. Okay, and so now we're doing the generalization of that for Dirac points, except we're saying that for the in-between planes, we don't have a Chern number, but we have a higher order TI index. And so I think the basic idea, which is not my invention, this is, you know, this is the original formulation of Fermi arcs, is that semi-metals, one way to classify them is to look at the insulating planes nearby. And then for each of those 2D insulating planes, you can ask about its 2D topological phase.
okay, last question. Yeah.
yes, suppose we introduce superconductivity in systems that it's not clear under what conditions high Fermi arc if like
Wait, sorry, I missed the beginning. If we introduced what? Oh, superconductivity. Okay, so the question, if we introduce superconductivity, what happens to the higher order Fermi arcs? I haven't thought about that. So I'm assuming that there's some generalized criterion. So we'd need to answer, how do we change the modulus of the Fermi arc? So there's always defined mod something, which is, well, I can explain to you how we fix the modulus. You maybe already know, but you need to determine the modulus of that. And you need to determine the trivial or topological phases of superconductivity. And once you do that, then the classification will follow through, but we have done it and I'm not sure if anyone has done it. So that's a great open question. And the great thing about superconductivity, which you probably were thinking, is that you have a whole symmetry. So these mid-gap states would be exactly at zero energy, which is of course much more elegant. That would actually promote them to be a proper 2D topological phase. So I think that's a really relevant and interesting question. Yes.
Okay, that's the same. Jennifer again. So next talk we will have Professor